All right, we are back. I have had way too much coffee, but let's work through all of these questions. What you want to remember is that you're going to differentiate with respect to time, and then apply the correction term, right? And you're going to do this twice. And the correction term basically accounts for the difference between differentiating with respect to arc length and differentiating with respect to time. So some specific examples, right? If we have, let me start farther up so I can write more on one board, right? So if we start with this formula, we have r cosine t, r sine t, right? So that's our toy example that we always start with because everybody's intuition tends to work well with the circle. All right, so first let's just calculate. First thing you want to do is just calculate the time derivative. Okay, so that is minus r sine t, and this is r cosine t. If I take the length of this, you can see that it's simply constant. It's just r. Okay, right. So then, for me to calculate at the first step, my tangent vector, right? So the velocity goes, if I draw my circle here, right, here's my position vector, x. And then here is my velocity vector, v, right? And t is going to go in the same direction as v, but potentially have a different length. Right? And so here we just divide, right? We just divide our derivative here by the length of the derivative, right? And so the r's inside here cancel out. In other words, keep doing that. All right. X prime over the length of x prime is simply equal to minus sine t cosine t, right? So the full velocity here is scaled according to r, but the unit velocity is not. Now, I know, right, that this is dx dt ds. And do you see what happened when I did this normalization? Right? The sort of the scale of things canceled out in some nice way, right? So that I'm now going around what looks like a unit circle, right? So I'm going now at kind of a standardized velocity of 1, right, around the circle when I go with respect to arc length, right? In other words, right, I can parameterize something and say go from time 0 to pi over 2, right? Or I can parameterize something with respect to arc length, right? And the arc length of this is exactly, say, pi over 2. I guess in our case we have this scaling factor r, right? And so all of this works out to be the correction term. Now we're going to go one step further, and we want to calculate, right, the curvature of, essentially the curvature of the circle. All right, so let's keep everything up to here, right? And we want to go one step further, right? So we want our kappa to be, right, twice where we do this operation where we differentiate with respect to t and then divide by this length. So we're going to differentiate, divide by r, differentiate again, and divide by r, and that's going to give us our kappa. Okay, so let's try it out. First, right, we want x prime of t normalized, which is this, right? Let's see. If you remember, what I got inside here, right, was just t. So I have this guy here, 1 over r, right, and then I have dx dt. So that's this vector here. And that's the same thing as I just computed. Now to go to the second stage, let's now make everything simpler. All right, so I have minus sine t, cosine t, and I want to differentiate it again and then divide by the velocity. In other words, I'm going to differentiate, right, compute a second derivative, and then I want to normalize by r. Okay, and if you do this, what you will get is 1 over r. When I differentiate this guy, I get minus cosine t. And when I differentiate this guy, I get minus sine of t. Right? In other words, my curvature vector, right, is scaled by 1 over r, and it points back in the direction, in this case it points back in this direction toward the center of the circle. Okay, and it has length r. So if I took the scalar curvature, right, it's 1 over r. And that's the curvature, that's always the curvature of the circle for any radius, right? And so this is how you compute it. In the other cases, right, in the other cases where you're dealing with straight lines, right, the answer should be obvious for what you should get for curvature when you crank it all out. So I'm actually gonna move on. Why don't you add some of, go ahead and do these like homework problems. You don't have to turn them in with your homework, but just go ahead and work on them individually, right? And then let's move on to curvature and tangent. So I just showed you, right, this simple case with the circle where I have my vector x, my velocity and tangent, right? So my tangent vector, which goes in the same direction of velocity. And I showed you that my curvature vector pointed back in this direction. Let me make it a different length. Right, so that was my kappa. And you see very clearly in this picture, and it holds in 3D too, that the tangent vector and the curvature vector should be orthogonal. It's not always the case that that the curvature vector goes in the same direction as the position vector, and we'll see a 3D case. So the reason that happens here is because everything is mushed into the plane, right? But it will always be the case that that the curvature vector is perpendicular to this velocity vector or this unit tangent vector. Okay, and all we really need to show here is that the dot product of these things should be 0, right? So that's a necessary, sufficient condition for this to hold. Okay, so we want to compute this. And here we use the fact that kappa right, that kappa is equal to the arc length derivative of the unit tangent, right? So we already saw that earlier. So we're just going to take now a dot product of, sorry, I need some water. Right, so we want to do kappa dot t, right, and we want to rewrite our kappa as the derivative of t with respect to arc length, and then we're going to take its inner product, right, with t. And we know a formula for this, like we figured this out. We know that to get this, we differentiate and then apply our correction term, right? So, right, so this is dt, right, the derivative of the tangent vector with respect to t, times our correction term, right, with this, which is this guy, and then its inner product with t. So in this case, right, we have the derivative of t with respect to t and the inner product with t. Now we use this theorem, right? If you go back in the notes, t is a constant length, right? We learned something about any function with constant length, that when you take its time derivative, it should be orthogonal to the original, right? Before we were applying it to the position vector, but here if we apply the same theorem to the unit tangent vector, so a vector that has constant length of 1, unit tangent vector. So we take the inner product of the unit tangent vector when it's with its time derivative, and this has to be equal to 0, right? So that tells us then, right, that when we calculate this kappa, right, that this inner product has to be 0. Okay, so they are orthogonal. I think I showed you before scalar curvature for the circle, right? So the scalar curvature for the circle is 1 over r for the circle of radius r. Okay. And then we have the normal vector to the curve defined in terms of the curvature vector. And here I want to go away from the case of this circle, because I want to avoid this case where the curvature vector or the normal vector points back toward the original point, because that doesn't necessarily always happen, right? So in the more general case, right, I have some point here, and maybe my position vector, right, is this x of t. Okay, and in this case, I have right, say my unit tangent going in this direction, and the curvature vector here, right, the curvature vector, we just showed that it has to be perpendicular to this. So it's going to make a right angle with that, right, with that tangent vector. And what it's telling us, it's pointing, as we go from, say, the point I've drawn to the next point over here, notice that the direction of the tangent vector turns. And kappa here is in some sense telling us the direction in which, right, in which this vector is turning as we go along the curve. So you see that it's starting to tip over. Okay, and so that force, right, that force is always applied orthogonally to the tangent vector, right? And so if we were to draw the tangent, if we were to draw the normal vector over here, so the kappa value for at this point, it would again be normal to the curve, right? So as we go along, the direction of the curvature vector is changing in response to the direction of the tangent vector, such that they're always orthogonal. Okay, and so just to finalize the material from this, right, from this lecture, we're going to move into three-dimensional space. Right? We're going to move into three-dimensional space here. And we're going to define a more complex situation. So let's see if I can come over to the slides here. Right, so we have learned about the position vector. So let me get a pencil and I'll draw that in white. Right, so here is my position vector that I'm working with. And so I have some point x of t at which I'm going to calculate all the quantities that we've discussed on the board. Right, so the tangent vector that I calculate, so to get the tangent vector, right, I differentiate with respect to t and divide by the length. So it's a unit vector in the direction of the velocity. And in this picture, we have it here drawn with this white vector. Okay, and again, these two vectors, the position vector and the tangent vector, do not need to be orthogonal. Okay. Except in that special case, right, where you have a unit length position vector, right? Okay, so we take again the derivative, right? So we take again the derivative of this tangent vector. So kappa, right, is the derivative of this tangent vector with respect to arc length. And now we're going to, and we just decided that kappa was orthogonal to the tangent vector. Okay, so now we're going to define a normal vector as kappa over its length. In other words, if you remember, we had a velocity vector and we made a unit tangent vector. Okay, now we have a curvature vector and we're going to make like a unit curvature vector. In other words, the magnitude of the curvature is not represented here. We just have the direction, right? We have the direction of the curvature vector, right? And so it follows that this normal vector is orthogonal to the tangent. All right, so if I go back to my picture here, right, I had my position vector going up, the tangent, right, points out here. If I want to draw my normal vector, I know, right, if I want to draw my normal vector, then I know it has to be orthogonal to the tangent. In other words, that there's a right angle right here between the tangent and the normal, right? We just showed that like for the circle, we showed it for a more generic curve, and this in 2D, and this is the 3D version. So we have a tangent and a normal that are perpendicular. Now we're working in a three-dimensional space, so there has to be a third dimension. Right, so thinking back to that circle, right, that spiral on the sphere, right? So I had that picture where there was like a curve and there was a spiral coming in. Okay, and in this case, my position vector goes from the center to say to some point. Okay, my tangent vector. Let me get a color here. My tangent vector is going to go in this direction. it's a little harder. It's a little harder to see, but it's actually going to, in this case, again on the sphere, it's going to point back toward the origin, and then we're going to have a third direction, right, with this, which is this guy. I'll do another example in a minute. This one is still sort of a special case because of this property of constant length means that the origin and the curvature vector are going to end up pointing in the same direction. Okay, but that's not a general phenomenon. But in any case, the point here is that we have. Right, we have these two. Let me draw a 2D case, and you can picture the third dimension coming up out of the board. Maybe that will help people out. Okay, so I have some point here. I have a tangent direction. I have a normal direction. So these are two vectors with unit length, right, that are perpendicular. And now I would like to define a vector that is perpendicular to both in 3D space, right? And because of the way I've drawn everything, that's going to go in or out of the board, right? So something that's going to be perpendicular to both the normal and the tangent. And we can get that, right? So we can get that very easily by simply defining, right? By simply taking a cross product of these two. And to do it in order, to do it with the correct orientation, you take the binormal and you define it as t cross n. And you can remember which order it goes in because t is based on the first derivative, right? So that's based on the first derivative, and that goes first. And this is the normal is based on a second derivative, and that goes second, right? And so that actually gives you a third vector. If I look at the curve or at the picture we've been playing with here, right? So I have my position vector, I have my tangent vector, then I have my normal vector, okay? And you can now see that this red vector, right, so let me go ahead and draw it for you. This red vector is what I get if I do this calculation, right? So I've written that binormal vector as t cross n. And now the situation on the sphere will make more sense to you. Let me actually go and draw on the slides again. If you notice, right, I have here my green vector, which is my position vector. Right, so if I look at where this starts spiraling around, okay, I have my position vector, and that's green. I have my tangent vector, and that one is blue. Okay. My curvature vector, right, my normal vector points back toward the center, right? So my normal vector is here. My tangent vector is this one, right? And when I calculate the binormal, what I'm going to have is a third vector, right, that points in this direction. And whether or not it points into the sphere, right, into the spirals or out of the spirals, you have to use the right-hand rule to figure it out. So in this case, right, if you want to picture this as the center of the sphere, right, and I'm turning it this way, when I apply the screwdriver, sort of a screwdriver or right-hand rule, I'm going to get a vector that points in toward the middle with this orientation of the vectors. All right, so that pretty much concludes what I wanted to tell you today, and I apologize for this unusual format, although I think it's not horrible. But anyway, let me leave you with one last definition, which is something called the osculating plane. Okay, and I told you how to get this. I told you how to get this binormal vector, but that's actually the binormal is the normal to the plane that contains, right, the tangent vector and the normal vector. So picture it slicing through the sphere along an equator, right? And the purple vector here, this guy, right? So picture the plane slicing through, and then this normal vector is this binormal. So that vector, the plane that slices through, is something called the osculating plane, right? And it has to be parallel to both the normal vector and the tangent vector. Okay, and then this binormal is the normal to that plane. Okay, so that concludes the lecture, and I will see about getting all these videos posted.